Okay, well, woohoo, we're on 7-2. Oh, what a great day we're having. Too bad you're missing out on all this great math while you're in wherever you are. And we are here in delightful Minnesota. So this is 7-2. We'll call this 7-2 part 1. This is Thursday, 3/22. And this will be the last recording. And then tomorrow will be our day of rest from having to kind of work a little extra as we were getting ready for the STEM trip club people to be gone. And so homework 7-1 is due on Tuesday, and the people who are in the room will just have a work day. And this is 2 variable linear systems. It is my expectation that this is all review for you. And but the thing I will kind of say is I'm hoping that you actually do the work of 7-2 a little bit to practice those, because you have the skills, but you maybe haven't done solving systems of equations for a while. And then our next thing that we're going to do is going to be, and I think it's our next thing, yes, multivariable linear systems is 7-3. So good thing the STEM Club people will be back for that and everything. But if you haven't practiced that, I'll just say it this way. When you have like 4 variables and 4 equations, it just gets a little messier. Do you know what I mean? It's that same process, but it gets a little messier. So if you've practiced and just kind of reminded yourself or brushed up a little bit at this point, then that can just make that a little bit just a little smoother for you. Because I will say it's one of those things in that next section that it's sometimes difficult to get the right answer, just because if you make a little arithmetic mistake, it just knocks you down. So this is 7.2, 2 variable linear systems is what my word would be. And we'll go kind of quickly through this. We'll do some problems, and I'll try to keep it to about 20 minutes. So we're going to use the method of elimination. You're already familiar with that, of linear equations in 2 variables. We're going to interpret graphically the number of solutions of systems of linear equations in 2 variables. We already kind of did a little pre-work of that. We know that there's either one solution if they intersect, infinite number of solutions if they're the same line, and no solution if they're parallel. But we'll use those words consistent, dependent, and independent. And then use systems of linear equations in 2 variables to model and solve real-life problems. So the first thing we'll do is this method of elimination, and I'm just going to kind of remind you of that, and then we'll do a couple of problems. I'll gauge myself by you as to if we want to do all the problems or a few or whatever. So the method of elimination. And then you have already done this. We just use substitution and graphing. Now elimination. If I'm lucky enough to have something like these 2 equations that are on the smartboard right now, the 3x and negative 3x will cancel out. So if I just add them together, I get 3y equals 6. Then y will equal 2. I can back substitute. That's kind of that way of saying that. We've always said substitute that back in and to get y. And I think the next slide might say that, and then back substitute to get the x value as you go through. So here is the method of elimination. Oops. And I'll just read through it quickly with you, and you decide kind of what you're writing for it. So the method of elimination, to use the method of elimination to solve a system of two linear equations in x and y, you perform the following steps. Obtain coefficients for x or y that differ only in sign by multiplying all the terms of one or both equation by suitably chosen constants. So that's where we just, multiply everything by something so that the x's are opposites or the y's are opposites. And then if you've correctly done that, then in step 2, you add the two equations to eliminate a variable and solve that first equation for a variable that is needed there. And then you back substitute that value you got into either of the original equations and solve for the other variable. And then we just check that the solution satisfies each of the original equations. Does it right? Oh yeah, it's a pencil. Okay. Does anybody need to see that anymore? If you need to see this, you can pause this recording and then go on as we do. And so this is the first example. It's a very straightforward example. The y's are going to cross out immediately, but I thought we'll do it anyway. And so our system is 3x plus 2y equals 4, 5x minus 2y equals 12. And again, it's already a situation where the y's are going to drop out. And so once you've written those, the y's are just immediately going to drop out. 3x plus 5x is 8x, equals 4 and 12 is 16. Divide by 8, x is equal to 2. Back substitute, it doesn't matter which equation you back substitute into. I'm just going to do the 3x plus 2y equals 4. So 3 times 2 plus 2y equals 4. 6 plus 2y is 4. Subtract 6, I get negative 2. 2y is negative 2. Divide by 2, I get y is negative 1. And so do make sure that you're putting your answer in an ordered pair if it works out. And we know that if these drop out and both equations or both variables drop out, then that's going to mean that they're either an infinite number of solutions or no solution, depending on whether it's true or false. And we haven't quite got that far yet. But we should just check that in there, and I'll just do it in my head. So 3 times 2 plus 2 times negative 1. 6 minus 2 is 4, and 5 times 2, minus 2 times negative 1. That's 10 plus 2. And that's 12. So it checks as we go. When you're going to really want to check things is when you have a lot more equations and unknowns, or you're taking a test or quiz or something like that. So just give me a head nod. That's like you've done that lots of times, correct? And so here's our next problem. And let me just kind of... Oh, there it is. Here's our next problem. For this one, you have to do some multiplying. Would you get the x's or the y's to drop out? It really doesn't matter. Anybody have an opinion? I would pick the y's as well. How come you picked the y's? Right, we pick the y's to drop out because we only have to multiply by 1. And one equation, yes, thank you for clarifying. We only have to multiply one equation by a number as we go. So take a minute, try that one, and we're going to multiply that by 4. I'll let you try that, and I'm going to give you a warning. The warning is that you're going to get fractions. Because sometimes when I give fractions personally, I think I did something wrong because I want it to be integers, but these are fractions. So I'll give you a little bit of time to do that. And I'm going to pause this recording while they do that, and then I'll start it back up. And so if you want to do the problem, make sure you pause also. Feel a little uncertain about what I'm doing. Okay. Oh, so I just said I feel a little uncertain about what I'm doing. But in the technology, turning the recording back on. So we just finished this, and if you are ready, otherwise pause this again, but we're going to the answer. And oh, just kidding. I did not have the answers on there. And so for this one, when we multiply by 4, it's 2x minus 4y equals negative 7, 20x plus 4y equals negative 4, 22x equals negative 11, and x equals negative 11 over 22, or negative 1/2. And then 2 times negative 1/2 minus 4y equals negative 7. Negative 1 minus 4y equals negative 7. Add 1, negative 4y equals negative 6. Divide by negative 4, y equals 6/4, which is 3/2. And we did check that hopefully as we went, and that does work. So there's that system of equations as we go. And this is just kind of going over a reminder that you multiply this. So when you look at these two systems that are right here, and I might just write in yellow because then I can be pointing to things. These were identically the same, but these are equivalent. Do you agree? They're not written exactly the same, but they're equivalent equations. And so as we think further along and having multivariables, we want to say to ourselves, what will make equivalent equations as we go, or equivalent systems? So this is specifically an equivalent equation, and these two systems are equivalent systems, and then they have the same solution set, and that's things that we can do. So what we can do, and this might seem unusual to you right now, but when we think about 4 equations and 4 unknowns, we can interchange 2 equations and the system is still equivalent. Do you agree with that? So, just moving the order of the equations. We can multiply an equation by a non-zero constant. That's what just happened in that last one, multiplying by 4. And then another thing that we can do is we can add a multiple of one equation to another equation in the system. And that's kind of what we've been doing to get that to eliminate. And we still have then that same solution as we go through that. So it might not seem like you care that much about that right now, but as we move on, we'll be interested in that. Now, we feel like we did awesome on number 3, so we're not going to do that one, and we're going to just skip that over and go on. So if you want to try number 3, you can, and then pause this right now, and then I'll write the answer and you can look at it. So pause it. And if you're coming back, here's the answer, 3, 2. And if you want to try that, fine. If not, that's fine also. We did not. Now, we are going to do another one, but this is the one we're going to do. And, my thought is, if you have something like that, it just makes me feel like I was using money. Does it make you feel that way? Yeah, because, I've got this, and it seems a little on the ugly side. So 0.02x minus 0.05y equals negative 0.38, and then 0.03x plus 0.04y equals 1.04. So I will ask for this example that you write that down just so that you knew what it started as. But does anybody have, an easy way to make this much more attractive? Yes, I can do that, but I just mean multiplying the top one by 4 and the bottom one by 5, and that'll get things to drop out. But then I still got all those decimals, do you know what I mean? Which just kind of lead me to making mistakes, personally, the Janet Jones problem there. So if I wanted to just make them look prettier for myself, what can I do? multiply everything by 100. And so before I even do anything, and this is optional, I would not have to do that. But if I multiply everything by 100, then I just get 2x minus 5y equals negative 38. And 3x plus 4y equals 104. And so do you agree with me that, it's just cleaner and easier to handle, and I don't have to think about my decimal places as much and things like that? So that's how I would do that one, and then I will go through that one. And since I had the suggestion of multiplying, didn't you say the first one by 4 and the bottom one by 5? Okay, we'll multiply that first one by 4 and the bottom one by 5. And when I do that, I'll get 8x minus 20y equals, what is negative 38 times 4? Say it one more time. 152. Negative 152. And then 15x plus 20y equals 520, I think, for that one. And then again, those are going to drop out. So 15x plus 8x is 23x equals, what's 520 minus 152? 368. And then when we divide by 23, I believe that should divide evenly. X equals 16 for that one. And then to back substitute, and I will comment that really I could back substitute into any of these. I'm probably not going to back substitute into the one with decimals, although I could. It wouldn't really matter. And I'll just back substitute into that first one. 2 times 16 minus 5y equals negative 38. 32 minus 5y equals negative 38. Subtract 32, negative 5y equals negative 70. Am I right? And then divide by negative 5, and y equals 1, 4. So I get 16, 14. And you have access to a calculator, so I would check that in the very original one, and it's just a matter of going 0.02 times 16 plus 0.05 times 14 and just seeing if that is the correct answer as we go. And then I have a little thing for you to try, and then I'm going to pause this again for that. And we know both the substitution and elimination methods, and so I gave a full sheet of paper, and I'm going to give you a little bit of time to try this, and then so I'll pause this for those of you who are maybe trying this on your own, or you want to just go through, you'll see that as we go. So you are writing answers to 1 and 2 in complete sentences. What are the differences between the two methods, substitution and elimination, and what are advantages of each method? When is this one great and when is that one great? And then I'd like you to try and solve that system for x and y with everything being variables. And it's a little challenge, but think about it. You've done that all the time, and so give a try for that. I will go over that system, but I want you to try it. And I'll pause this again and then pick up when I'm ready to go over that. Okay, well, we've had a few minutes to try and answer those first two questions and then find a general solution. We talked about the fact that if we can find a general solution and we needed to solve 100 of these in 5 minutes, we could just enter in a computer program we would maybe write the coefficients A, B, C, D, E, and F, and it would immediately tell us what X and Y are. Because here's how we can do that. And I'm going to just use elimination, and I multiplied the first equation by negative D and the second equation by A. And, just that's how I'm going to make the X's drop out. Oops, I put my parenthesis in the wrong spot. And y equals c, and dx plus ey equals f. By all means, help me if I make a mistake, because I tend to sometimes make mistakes. And I try to put my letters in alphabetical order, not x and y last, just so that I can see like terms. So this will be negative a dx minus b dy equals negative CD. And this one is ADX plus ACY equals, oh, this is an E. Thank you. Yes, E. Very good. Equals FAF. And when I add those two, these cancel, and I get, and I'm going to write this bottom one first, AEY minus BDY equals, and I'm going to write AF minus CD. Do you see the common factor of y on the left? And so I'm going to say this is AE minus BD y equals AF minus CD. And then to get y alone, I'm going to divide by AE minus BD, AE minus BD. And I'm going to get y equals AF minus CD over AE minus BD. And so really, if I know those coefficients, that's a pretty easy math problem, really, right? And so I can figure that out. I did do back substitution, and it's just a lot more letters. But the real way that I did this is I took this ax plus by equals c and dx plus ey equals f, and I multiplied each one by, and I think I did positive e there and negative b there, minus b there. And then when I distribute that, I get aex plus b e y equals CE, and I get minus BDX minus BEY equals minus BF. And then when I add those, the BEYs cancel out, and I get AEX minus BDX equals CE minus BF. Oops. And then I'm going to distribute out the x, and AE minus BD times x equals CE minus BF. And then when I divide by AE minus BD on both sides, I'm just going to get x equals CE minus BF over AE minus BD. So if you think of that from a programming standpoint, that's a pretty easy problem. You would tell somebody input, tell me what A, B, C, D, E, and F are, and then I will just do this calculation, and that will be the way that I'll have that solution. So CE minus BF over AE minus BD, comma, AF minus CD over AE minus BD. And we want to kind of start in our lives thinking about the interconnectedness. Do you know what I mean? Of like, really, when you do a bunch of these solving systems, you're doing the same thing all the time, aren't you? You know, essentially, you're doing the same thing all the time as you go through that. So the thing that I'm going to leave us with right now is graphical interpretation of solutions. And here we're going to graph things. And I'm just going to remind you that these are our graphical interpretations, and I'm going to name them as well. And I wish I could kind of write this along there, but I can't fit it in. So here's what can happen when we have a system of two linear equations in two variables. And so we can either have exactly one solution, and the two lines intersect at one point, and the slopes of the two lines are not equal. And so that is the exactly one solution. And those are called consistent. Consistent solutions mean there is at least one solution. That's consistent. at least one solution. And they're also called independent if there is exactly one. And independent, which is exactly one solution. So that's all this first one. They intersect at one point. Their slopes are not equal. The second situation is there's infinitely many solutions. And I don't remember if we've done this before, but this year we will we'll write those in terms of each other when we give our answer. The two lines coincide or are identical, and their slopes are equal. And if this has an infinite number of solutions, so you don't have to write that again, but then it's called consistent, but it's called dependent because, you know, one depends on the other, and that's when it has an infinite solution, set of solutions. And dependent, and that's the infinite solutions. And have we covered that before, maybe or in your past math classes ever? It often comes up. We don't spend a lot of time. And I think on your next test, you'll have to tell if things are consistent, independent, dependent. And then our last case is when there's no solution, the lines are parallel, and the slopes are equal. And I'll just write no solution here. And they're not called consistent. They're the opposite of that, inconsistent. Inconsistent. And then that's no solution. Just as kind of a little reminder. So that is it for our lesson today, and that is all the lessoning we'll do until next Monday, just to kind of let everybody know.